The sun has been a significant area of strength for us, especially of late, and it will undergo a basic and fascinating change: the inversion of its magnetic field. This phenomenon occurs generally at regular intervals, marking the midpoint of the solar cycle, and has broad repercussions for us here on Earth. In fact, the potential for the sun to present a serious gamble could cause complete disruption and calamity for everyone in the world. The sun's magnetic field is generated by the movement of electrically charged gases in its interior, a cycle known as the solar dynamo. Over the long term, this magnetic field becomes increasingly complex and reshaped due to the sun's transformations and convective changes. Ultimately, this process leads to a complete inversion of the magnetic poles. The north magnetic pole changes into the south magnetic pole, and vice versa. So, how do we analyze the entire cycle and investigate the sun? The sun is primarily composed of hydrogen and helium in a plasma state, where electrons are not bound to atoms, resulting in a combination of free electrons and ions. Its interior is divided into several layers, with the core at the center, encased by the radiative zone and the convective zone. The core is the sun's most significant region, where nuclear fusion occurs, converting hydrogen into helium and releasing vast amounts of energy. Surrounding the core lies the radiative zone, where energy is transferred outward through radiation. In this space, energy moves slowly outward as photons are absorbed and re-emitted by the solar plasma. The outer layer of the sun's interior is the convective zone, where energy is transported by convection. Hot plasma rises to the surface, cools, and sinks again, creating convective flows. The solar dynamo process operates mainly in the convective zone and a thin layer called the tachocline, which lies between the radiative zone and the convective zone. The tachocline is critical because it's where the sun's differential rotation and shear flows play a fundamental role in generating the magnetic field. Here's something intriguing. The sun does not rotate as a solid body. Rather, different parts of the sun rotate at different rates, with the equator spinning faster than the poles, a phenomenon known as differential rotation. This differential rotation stretches and twists the magnetic field lines, enhancing the magnetic field. The solar cycle lasts about 11 years, during which the sun's magnetic field undergoes a series of changes, culminating in a pole inversion. This cycle is driven by the solar dynamo and includes several phases. At the beginning of the solar cycle, the sun is in a state known as solar minimum, characterized by a low number of sunspots and minimal solar activity. The magnetic field is generally simple and bipolar, with a distinct north and south magnetic pole. As the cycle progresses, the number of sunspots increases. Sunspots are regions of intense magnetic activity and are associated with the emergence of magnetic flux from the sun's interior. These sunspots appear in pairs with opposite magnetic polarities and migrate toward the equator over time. Around the midpoint of the solar cycle, the sun reaches solar maximum, a time of peak activity with the highest number of sunspots, solar flares, and coronal mass ejections, CMEs. The magnetic field becomes incredibly complex and tangled due to the ongoing twisting and shearing from differential rotation and convection. As the solar maximum fades, the magnetic field begins to reconfigure itself. The reshaped and tangled magnetic field lines reconnect, and the global magnetic field gradually switches its polarity. The north magnetic pole becomes the south magnetic pole and vice versa. This cycle is facilitated by the movement and reconfiguration of solar plasma. After the pole inversion, the sun enters a phase of declining activity, returning eventually to solar minimum. At present, we're in the solar maximum stage, and the sun's magnetic field is poised to flip. During this stage, we can expect to see solar activity that could be as risky as it is captivating. However, the sun's magnetic field inversion isn't a sudden flip. It is a continuous cycle. As the solar cycle progresses, the sun's magnetic field undergoes a series of transformations. Currently, the magnetic field is at its most twisted and tangled state, approaching a tipping point that leads to its reconfiguration and eventual flip. So, how do we know when the sun's magnetic field will flip? Researchers monitor the sun's magnetic activity using various instruments and methods. Observatories equipped with powerful telescopes, both on Earth and in space, provide detailed images of the sun's surface and its sunspots. Instruments like the Solar and Heliospheric Observatory and the Solar Dynamics Observatory measure the sun's magnetic field and its changes over time. One key indicator of an impending magnetic inversion is the behavior of sunspots during solar maximum. Sunspots appear more frequently and become more pronounced as they move toward the sun's equator, signaling that the magnetic field is becoming more unstable and preparing to flip. Let's delve a bit deeper into sunspots. When the sun's magnetic field lines become twisted and tangled due to differential rotation, the sun's equator rotates faster than its poles, causing the magnetic lines to stretch and twist. When these lines loop over the sun's surface, they inhibit the convective movement of hot plasma from the sun's interior, resulting in the cooler, darker patches we observe in sunspot images. Sunspots are not just intriguing solar features. They can also produce strong solar flares and coronal mass ejections, CMEs. These phenomena release immense amounts of energy and charged particles into space. When directed toward Earth, they can disrupt satellite communications, impact power grids, and pose dangers to space travelers. Increased solar activity can enhance auroras, but can also raise radiation levels in Earth's upper atmosphere. Now, let's examine the differences between solar flares and coronal mass ejections, CMEs. While both are enormous eruptions of energy from the sun, they differ significantly. Solar flares are sudden, intense bursts of radiation caused by the release of magnetic energy associated with sunspots. They emit a colossal amount of energy and light, often as X-rays and ultraviolet radiation. Think of them as explosions of brilliant light and heat on the sun's surface. In contrast, CMEs are massive expulsions of solar wind and magnetic fields from the solar corona. They can be viewed as giant bubbles of gas and magnetic fields being released into space. When a coronal mass ejection occurs, it sends billions of tons of solar particles into space at extremely high speeds. While solar flares and CMEs are related, they are not the same. A solar flare can occur independently, but sometimes, a particularly strong solar flare can be accompanied by a CME, although a solar flare doesn't necessarily cause a CME. In terms of risk, solar flares can disrupt radio communications and navigation signals, presenting a significant danger to space travelers due to the extreme radiation. On the other hand, CMEs can have a more widespread impact. They can cause geomagnetic storms that disrupt power grids, satellite operations, and navigation systems. CMEs can also enhance auroras but pose serious risks to Earth's technology and infrastructure.
Another consideration is that during periods of high solar activity, the amount of radiation reaching Earth also increases. Satellites and other space vehicles are particularly vulnerable to heightened solar activity, as the charged particles from the sun can damage electronic components, disrupt communication signals, and even alter satellite orbits. Beyond harming technology and infrastructure, what else can happen to the planet? While the sun's magnetic field inversion does not directly affect Earth's climate, the associated changes in solar activity can have an impact. Some studies suggest that variations in solar radiation can influence atmospheric conditions and weather patterns. For instance, increased solar activity can lead to a slight warming of Earth's atmosphere, potentially exacerbating existing climate change. Could auroras be the only positive aspect we experience here on Earth? Perhaps one of the most striking impacts of increased solar activity is the enhancement of these magnificent lights. These natural light displays, known as the northern and southern lights, occur when charged particles from the sun interact with Earth's magnetic field and atmosphere. We often hear about the aurora borealis, but these lights can also be seen around the South Pole. During periods of high solar activity, auroras become more frequent and can be visible at lower latitudes, providing stunning nighttime displays. However, beyond the beautiful auroras, there are additional unsettling aspects of the sun's magnetic inversion that could occur if we are ill-equipped. One of the primary dangers associated with the magnetic field inversion is the increased likelihood of geomagnetic storms. These storms occur when solar wind overloaded with charged particles interacts with Earth's magnetic field. In extreme cases, they can cause widespread power outages and damage communication systems. One such event occurred on the morning of September 1, 1859. Astronomer Richard Carrington was observing the sun through his telescope when he witnessed a brilliant flare of white light emanating from a group of sunspots. This event, now known as the Carrington Event, marked the beginning of the largest geomagnetic storm ever recorded. The white light Carrington saw was a massive solar flare, an intense explosion of radiation caused by the release of magnetic energy stored in the sun's atmosphere. This flare was so powerful that it triggered an enormous coronal mass ejection, CME, directed toward Earth. The CME reached Earth in just 17.6 hours, a remarkably short time frame considering the sun is 93 million miles away. When the CME hit Earth's magnetosphere, it triggered an incredibly strong geomagnetic storm. The effects were swift and far-reaching, disrupting Earth's magnetic field and inducing currents in the ground. Moreover, transmission lines, critical for global communications at the time, experienced extreme disturbances. Sparks flew from transmit machines, operators received electric shocks, and some telegraph stations even caught fire. The induced currents were so powerful that operators could send and receive messages even after disconnecting their batteries. One of the most striking and visible impacts of the Carrington Event was the spectacular display of auroras. The auroras were so bright and widespread that they were visible far beyond typical polar areas. People as far south as the Caribbean, Mexico, and Hawaii reported seeing the sky illuminated with vibrant colors. The auroras were intense enough that they lit up the night sky, allowing people in the northeastern U.S. to read newspapers by their light. In the Rocky Mountains, gold miners were allegedly awakened by the brightness, mistaking it for dawn and starting to prepare breakfast. Individuals described the sky as having glowing red, green, and purple shades moving and shimmering across the horizon. Now, imagine if a solar storm of the magnitude of the Carrington Event were to strike Earth today. The results would be devastating. The sun is undergoing a significant transformation with the reversal of its magnetic field, an interaction that happens roughly every 11 years as part of the solar cycle. This event, driven by the solar dynamo, could have far-reaching consequences for Earth, potentially causing disruption and disaster. The sun's magnetic field is generated by the movement of electrically charged gases in its interior, creating a complex magnetic field that ultimately switches its polarity. The sun is primarily composed of hydrogen and helium plasma, with energy produced by nuclear fusion in its core. This energy moves outward through the radiative zone and then by convection in the outer layers. The solar dynamo system, which operates in the convective zone and the tachocline, produces the sun's magnetic field. Differential rotation of the sun, where the equator spins faster than the poles, stretches and intensifies the magnetic field lines, driving the solar cycle. Currently, the sun is in the solar maximum phase, where sunspots and solar activity are at their peak, potentially causing risks like solar flares and CMEs that can disrupt satellite communications, power systems, and pose dangers to space travelers. Researchers monitor the sun's magnetic activity and sunspot behavior to predict when magnetic field inversions will occur. Sunspots, which result from tangled magnetic lines, can produce solar flares and CMEs, both massive releases of energy that affect Earth in different ways. While solar flares emit radiation, CMEs release tremendous amounts of solar particles into space. These phenomena can enhance auroras, but also present critical dangers to Earth's technology and infrastructure. The sun's behavior is an intriguing interplay of material science and natural phenomena, affecting not only our solar system but also life on Earth. Understanding the intricacies of solar activity is crucial, especially as we continue to rely on technology that can be influenced by solar events. The sun produces energy through nuclear fusion, converting hydrogen into helium and releasing immense amounts of energy in the process. This energy travels through the various layers of the sun, eventually reaching the surface and radiating into space. Solar activity can manifest in various forms, including sunspots, solar flares, and coronal mass ejections. Sunspots are cooler regions on the sun's surface caused by magnetic activity, appearing as dark spots. These changes in solar activity follow an approximately 11-year cycle known as the solar cycle, where periods of high activity, solar maximum, are followed by calm periods, solar minimum. During solar maximum, the number of sunspots increases, leading to more frequent solar flares and CMEs. Solar flares are sudden eruptions of energy that release radiation across the electromagnetic spectrum, including X-rays and ultraviolet light. These intense bursts can disrupt radio communications and pose risks to space travelers. In contrast, CMEs are massive emissions of solar wind and magnetic fields that arise from the solar corona and are ejected into space. When directed toward Earth, these releases can cause geomagnetic storms that disturb the planet's magnetic field, leading to beautiful auroras, but also potential disruptions to technology.
The impacts of solar activity extend beyond space. They influence Earth's atmosphere and surface. Studies suggest that variations in solar radiation can affect weather patterns, possibly contributing to climatic anomalies. Increased solar activity can also lead to atmospheric warming, which is a significant factor in discussions about climate change. Moreover, the potential for technological disruption due to solar storms cannot be underestimated. A severe geomagnetic storm could damage electrical grids, disrupt satellite operations, and affect navigation systems. Preparing for such events involves monitoring solar activity and developing strategies to mitigate their impact on infrastructure. Scientists continue to study the sun's magnetic field and its cycles to better predict when significant solar events may occur. This research involves a combination of ground-based and space-based observatories that track sunspots, measure magnetic fields, and analyze solar wind. With ongoing advancements in technology, our ability to anticipate solar activity improves, which is essential for safeguarding our technological infrastructure and ensuring the safety of space travelers as we explore space. As we focus on the sun, its influence on Earth becomes increasingly evident, from the dazzling displays of auroras to the potential challenges posed by solar storms. The sun remains a powerful force in our solar system, and understanding its cycles and behaviors not only enhances our knowledge of astrophysics, but also prepares us for the effects of solar activity on modern life.